Okay, let us start, right? So I'll try to use 5 minutes to finish what I didn't finish last time, and go on to our first lecture in regression. So as a recap for what we discussed last time, I'm sorry I started 3 minutes early, but as a recap of what discussed last time, when Y is noisy, right, we have different approach to do things. The first approach is when Y is noisy, then the first approach is we first learn Py given X, the probability distribution, conditional probability distribution of Y given X. And then the second step is based on our estimated Py given X, we can generate a prediction of Y hat. Right? This step, we estimate the underlying conditional distribution by minimizing the KL divergence. Right? So our loss function in this case is we use the KL divergence as a loss compound function or cross entropy. Right? Same thing. Right? Cross entropy loss. Okay? By minimizing this loss, what we're doing is also maximizing the likelihood. Right? So this is our origin of MLE. You can put that in a coherent framework of understanding, right? The second step, where we get our predicted sort of estimated P hat, we can use it to generate a single prediction Y. Now, in this step, we can use a different loss function. Depending on whether our Y is discrete or whether it's continuous. It's continuous, we typically use L2, L1, right, loss function like that. And when it's discrete, we use 0, 1 loss. We also can change the 0, 1 loss into different penalties for different type of error, depending on what our need is, right? So the loss function here and loss function here could be different, right? Because they are separate stage. A student just asked me just now about KL divergence. So let me reiterate the idea of introducing KL divergence. Because traditionally, when you were taught MLE, the MLE was taught as if it's a sort of like a separate idea from the way, for example, you do linear regression, right? So when you do linear regression, you are minimizing the expected Y minus beta X squared. You're minimizing this to find out beta. When you do MLE, you are maximizing something, right? You're maximizing the likelihood. It looks like they're a different thing. What I want to say in my last lecture is that we can put them in a single coherent framework where we are both minimizing something. And what we minimize is our error function. And what this error function is basically the expected loss function, right? And they're directly trying to find a function f. Okay? So let's just write y equal to fx plus. And I just want to find the optimal f that helps me to directly give me an x and predict y, right? So here, based on my estimated f hat, then I immediately have my y hat. So instead of estimating conditional probability, I directly find a function that helps me to best predict y hat. Now, if in this approach, if we minimize L2, then suppose forget about model, right? Suppose I want, what is the function f that minimize the L2 in the underlying population that minimize L2 among all functions? If our model is the model of all functions, possible functional forms, what is the function form that minimizes L2 in the underlying population? Well, it turns out that it's basically EY given X. Okay, right. So then, if we actually estimate model, use a more limited model, right, like a linear model, to estimate this function using observed data, then what we're doing is we're essentially finding out a approximation of EY given Y hat. So our estimated F hat, you can think about this approach as our estimated F hat is an estimation or approximation to the underlying C. This is called CF, okay? CF, which is also called a regression function. Now let me so let's see this. Now, suppose this is x, this is y, and let's say this is the underlying population, right? Or maybe observed points. Actually, it doesn't matter. The first approach is to try to estimate the So these things are py given x. So the first approach is I try to estimate py given x, right? Given each x, the conditional distribution of y. And then use my estimate py given x, I form a prediction of y hat. Right? That's the first approach. The second approach is try to directly find a line, right? Directly find a line that helps me best predict y given x. So these are the difference between the two. In the discrete case, in terms of classification, sorry. So in the case of classification, when our y has discrete values, then the two approaches I think it's also very easy to explain here. The first approach is to estimate the probability of this point being being 0 or 1, right? So suppose this is 0, this is 1. Then the first approach is estimating the probability of a point being 0 or 1 here, and then based on my estimate probability, for example, 45% versus 55%, I make a prediction. Right? So that's the first approach. The second approach is directly finding a function line, which is a line, okay? A line that can separate these two. I don't care about underlying probability. Let me just find the best function that separates the two, because that helps me make predictions. So there's a difference between the two approaches. I will begin today with a third approach, which is a more sort of a cumbersome or difficult approach to do, which is estimating the whole joy distribution of Pxy. Okay? I forgot about this. Okay. So the first approach, like we said, is estimating Py given x. But what if we can just estimate the entire joint distribution? If I can estimate Py and x, right, the joint distribution of Pxy, then why not do it, okay? If we do that, then we get P hat xy, right? That's our estimated probability. And from this joint distribution, I can always calculate P hat y given x, right? So if I have this, I always have this. It's very easy. So, and once I have this, I'm back to my first approach, and I can use this to generate a y hat. Right? So based on the joint distribution, I can always calculate the conditional, and then I can give you a prediction like that. So maybe your question is why? Why do we even bother to do the joint distribution if we can just start here? Why do we even bother here? Well, first of all, before talking about why bother, let me just say there's a name for this third approach, which is distinct from the first two, and this name is called a generative model. Okay, generative approach. So this approach, estimating the joint distribution, is called a generative model, and the other two, the first two that I mentioned, is called discriminative model. The idea is generative model is a model that estimates the joint distribution of all the variables in our application, right? In our model. The discriminative model is conditional on x. So either given x, let me directly predict y, or given x, let me estimate Py given x first, and then generate prediction. Whatever has to given x. Okay, so x is given in the discrete model. In the generative model, we estimate the whole joint distribution. Now, one of the benefits of generative model that discrete model cannot do. The first thing we establish is once I estimate the general model, I can always use it to generate a discrete model, right? So given Pyx, I can always use it to generate Py given x. But why do we do the additional step? So one benefit of estimating a generated model is that once I have the joint distribution of Pyx, I can use it for simulation, okay? Meaning generate new data points. So suppose your observed data is x1, y1, right? All the way to xn, yn. Suppose this is your observed data. And that's all the data you have. Can I generate new data based on my estimation? Well, if you estimate py given x, suppose you only have this one, then yes, you can generate new data, but you can only generate x1. But based on the value of x1, the same x1, you can generate more y. Okay, you can generate more y from this distribution, right? So if this distribution is something like that, then given the value of x1, then you can always draw new y values from this distribution. What you cannot do is generate new x values as well, because you do not know the distribution of x. You only know the distribution y conditional x. You do not know how x and y jointly what their probability is. So you cannot generate new x values. You can only generate new y values, but keeping the original x values, right? Conditional on the original x values. So how do you generate a new x and y value? If I want to just simulate more xy, okay? More xy data, just simulation. How do I do it? Then you have to have a generative model where you basically estimate the joint distribution of PRs. And so simulation is a key sort of a functionality of using a generative model, right? So once you have generative model, you can do simulation and you can generate new data. So these data are called synthetic data because they're not real, right? Synthetic. And they're based on your estimated joint distribution. Now, there's one very, very, very important generative model, one type of generative model, which is scientific model, right? So every scientific model, in economics, we also call them structural model, which I already described in my introduction. Every scientific model you have in natural science or in economics or economic theory or structural models, they are generative. They describe how both x and y are generated, right? They are not conditional. They're not discriminative. Given x, what is y? They are generative models, and they are not only simple generative models, but they are generative models that describe the causal mechanism. So we say scientific model is an important type of generative model that describe the causal mechanisms that generate the joint distribution pxy. Okay. Now, of course, scientific models, as a special class of generative model, of course, they can be used for prediction as well. Right? Truly successful scientific model is the best at making predictions, the most precise predictions. But learning causal mechanism, the goal of learning causal mechanism, as we have already discussed, is distinct from the goal of making predictions. Right? Now, so here's a simple example of scientific versus statistical model. Or you can think about that as scientific model versus discriminative statistical models. So suppose we want to predict where Mars will be in the night sky. I just want to predict the location of Mars. Well, I can do this with a statistical model. I don't have to have a scientific model. I can have a simple model where, for example, I assume that Mars revolves around the Earth. I can assume Earth is the center, and I can assume Mars goes around the Earth, and then I build a simple model like that, and I can use it to predict the location of Mars in the night sky. It would work perfectly well for my purpose, because my purpose is easy, simple, which is simply predicting the location of Mars. I don't care about whether my model is scientific or not. I don't care whether it's correct. I don't care whether it truly describes the causal mechanism. I just want it to work. Okay, given me X, predict Y. Right? Now, of course, if you want to understand the underlying causal mechanism, then you need to build a scientific model in which obviously, the Mars does not revolve around the Earth. Right? So that's a simple example to illustrate that. Okay. Now, one of the other sort of feature of scientific model is that we can learn this model using all kinds of various kind of different data, right? Sometimes very different data. So I mentioned this point in my introduction as well. Basically, anytime we have different data, but you believe they're generated from the same or very similar causal mechanisms, then you can use this single scientific model to fit both kind of data, because both data can inform you on the values of parameters in that model, right? And these data can be very, very different. So I think I already mentioned this point in my introduction. So for example, whether you can learn if you believe that a single risk aversion utility specification describe different behavior, describe a person's investment behavior, describe a person's betting behavior, his career choice behavior. If you believe that, right? If you believe in your utility specification, then you can look at the data on a person's investment behavior and look at data on a person's, let's say, labor supply behavior, and then you can combine those data and to both estimate your underlying risk aversion parameter. So that's a feature of a scientific model because it's able to link very different data sets if they share similar underlying causal mechanisms. Right? Okay. All right, so that's so much about what I want to discuss in my first lecture. Regarding scientific model, and especially regarding structural model, obviously we're going to I have already discussed them in my introduction, and we are going to do them again in the second part of this course when we talk about causal inference again, right? So we're going to spend more time on this topic. Right now, I just want to give you an overview of different ways of generating predictions. Two are so-called discriminative, which is given x, let's generate a y, let's predict y. The other is generative, which is estimating the joint distribution, and obviously we can use it for prediction purposes as well, right? Okay. Now, finally, I want to mention, so that's so much for my introduction on the foundation of statistical learning. This is really a lecture that combines many different elements. The beginning part, right, when I discuss growth functions, VC dimensions, generalization bound, this part is called a learning theory. And if you're interested in learning more about this part, there is an excellent textbook, which I really recommend. Just here, right? The Abu Mustafa from Caltech and two of his co-authors wrote this book called Learning from Data, which is really excellent, very well-written book, to which my slides are also indebted to. Right? So I highly recommend you do learn more from that book if you're interested. And here's a link. Go to resource. So you can go to the course website. They also have many lecture videos you can read, you can watch, and you can purchase the book if you can.